Yeah, now it's already done. Live streamed, okay?
Yeah, okay, it is done. Yeah, it is done.
Yeah.
So, good afternoon to everyone. Sorry, I was not there.
Now, this kind of message we getting earlier also, but I was confused because this was the first time I am getting this kind of 6 digits. Otherwise, it will be just 2 digits.
Yeah.
Okay, so let's start successfully.
Please.
Good live stream.
Yeah.
Good afternoon, everyone. So welcome all to the lecture series on atmospheric dynamics and its applications to climate sciences. This is the 5th lecture in the series, which will be delivered by Dr. P.N. Sen sir, who is a visiting professor in SPPU, Savitribai Phule Pune University, Pune. Before we start with the lecture, I would like to request Dr. Ghulam Rasool, member EC SAMA from Pakistan and former DG PMD, to please give his welcome address. Sir, please.
Thank you very much. It's a matter of great pleasure and honor for me to welcome you all to lecture number 5 on atmospheric dynamics. I would like to appreciate the efforts of Professor Ajit Tyagi and Professor Das to arrange such lectures, lecture series on different topics of meteorology and climate sciences, to provide knowledge to the non-meteorological professionals working in agriculture, biodiversity, water, and so many other fields, because there is a growing concern of climate change, and understanding the climate science complications that provides a great vision to the people who are already engaged in studying impacts of climate change on different socioeconomic sectors. So this is a great initiative which I would like to appreciate, that from SAMA platform, not only SAMA member countries are benefiting, even the other regions are also benefiting. There is a growing interest of attendees. Today, I was told that 1,140 people from 51 countries have registered for this lecture. This is great, really appreciable. And on the average, 250 to 260 participants are attending these lectures. This is a great number. And people from different walks of life who are interested in application of climate sciences, they are benefiting from this knowledge platform. This is owned by its member countries, and sometimes there are excuses that some member countries are not taking good interest, including me. Including Pakistan. Yes, I admit that there was inertia in our attitudes, but we are with you, and you are our brothers. You are seniors like Professor Ajit Tyagi and Professor Rathore. We pay a lot of respect, and we are with you with this initiative from the first day. Sometimes there are slacknesses, but we will try to overcome those. And this platform should be further energized. Very great occasion that I would like to commend the efforts of Professor G. Tyagi and Professor Das, their dynamic leadership and their contacts. They are bringing resource persons of credible nature, and they are covering the science of meteorology in such a nice way that simplified messages, simplified terminologies, simplified way to digest this science, because everybody is not graduated in climate sciences. So appreciation goes to the resource persons also, how they simplify this complicated science for the non-meteorological professionals. And there is the growing interest in these lectures is showing that they are getting a lot of benefit from these lectures. Professor Sen is delivering today on atmospheric dynamics. So very good topic, and its constituents, especially scale analysis and those equations, simultaneous solution of those equations which are governing atmospheric motion. So that will be very interesting lecture, of course, and that will provide the basis to numerical weather prediction. Numerical weather prediction is simply computerized weather prediction. I remember those days when New Delhi, Karachi, Tashkent hubs were receiving data, and those data were then plotted on paper charts on different stations. Then meteorologists was drawing lines of isobars to locate high pressure, low pressure areas, likewise upper air data. And now this science is progressed to the next step of numerical weather prediction, in which data sets are received by the computers directly, and they are then operated to produce outputs on different time steps. So great. Let's move to Professor Sen, and I will join for a few moments, and I will enjoy this lecture. Thank you very much, Professor Sen. Thank you very much, Professor G. Tyagi and Professor Das, and all the attendees. Wish you good luck and great knowledge sharing from this platform. Thank you.
Thank you very much, sir. So now Professor Sen sir has already delivered this an inaugural lecture also, and we had introduced sir. Sir is now a visiting professor in Department of Atmospheric and Space Sciences, Savitribai Phule, Pune University. So now I request Sen sir to please share his screen, and he can start with his lecture.
So today's topic is concept of order of magnitude and scales of atmospheric motion. So this is a very important topic. Now, motion of the Earth has one of the greatest influences of human life, controlling the climate, rainfall, weather pattern, etc.
Sir, 1 minute. We cannot see your screen. Did you share the screen?
Okay, just 1 minute.
Meanwhile, Dr. Mohan Kumar Das has joined. So, good afternoon, Dr. Mohan.
Hello everyone.
Yeah.
Yeah, we'll see it. This is the eastern part of Bangladesh. In the August monsoon, the area was fully inundated due to the huge monsoon flood. So today we came with a team for the visiting that place. Thank you.
Okay.
Happy
Yeah.
to see you, PN sir.
So, sir, yes, we can see. Yeah.
We are able to see it.
Yes, sir.
Just one. Just 1 minute, I will adjust a little bit.
Yeah, we can see now, sir.
I will see that, I will adjust a little bit the screen. So the motion of the earth has atmosphere has the greatest influence. It creates it's got a lot of influence on the human lives. It controls climate, rainfall, weather patterns. And this is mainly due to the differences of incoming solar radiation and also the other factors like topography, land sea contrast, and especially the most important thing is the rotation of the planet. These factors control the local scale, like between a mountain and a valley, a larger scale, major storm systems, and global scale, determining the prevailing wind direction for the entire planet. All these circulations are governed by the similar physical principle. Physical principles are same, but they are some forces are present in some places, some forces are not very present in that places. Now, atmosphere, the mass of the air surrounding the earth bound more or less permanently to the earth gravitational attraction. But it is the most unstable part. These processes contribute to the variability of the climate system on a wide range of spatial and temporal scale. Now, what happens? Meteorologists, they are classifying according to their size. So one's a small gust, tiny gust to a giant storm. So these are called scales of motion. Now, the atmosphere is a large variety of both spatial and temporal scales. Efforts have been made to various say phenomena and scale. The class describing the longest light phenomenon known as the planetary scale, and to the other end of the spectrum is the microscale. So which is of only few centimeters and a few minutes or a few seconds or so, very shortly. Now, particularly in this area, our area, these 9 countries which are having, particularly during the summer, sometimes we see some small, say, the air moving and some lips moving. That is a very small scale system. That is the weather does not produce any weather as such, but such things are also occurring. That is a very small size, and it stays only for a few minutes or a few seconds. And there is also large, also very different size and large area. Now, this figure will give you some idea about the thing. Not that this is the gospel truth. There are some differences also. Now, if we look at this diagram, on the x-axis we have got the time scale, lifetime, and on the y-axis we have got the says space scale. So we have got different small turbulent eddies, then thunderstorms, tornadoes, waterspout, then land sea breach, mountain breach, and all these things, hurricane, then mid-latitude high pressure and low pressure, then weather fronts, then waves. So all these are different. They are having different sizes and their lifetime is also different. But sometimes they are not exactly that much, that the boundary is not that rigid. There are some, say, porous boundaries. So actually it can be classified into 4 classes: global scale or planetary scale, then synoptic scale, mesoscale, and microscale. Planetary scale and synoptic scales are sometimes called megascale or dark scale. There is another scale known as climate scale, which is the time scale of the order of decades and beyond, centuries also. So planetary scale or global scale is the largest and generally spans tens of thousands of kilometers in size and extending from one end of the world to the other end of the earth. And global or planetary scale including the impact large areas of globe and last for weeks and even months at a time. Now, some of the examples are intertropical convergence zone, ITCZ, monsoon trough, Rossby waves, jet stream, then trade winds, mid-latitude westerlies, and so etc. All these are this. Then another important thing is subtropical high pressure belt. That the position of the subtropical belt and the subtropical highs and their strength also change the weather across the globe. Now here I will show you one diagram that is our ITCZ, which is covering the entire globe. And there are 2 ITCZ one you can see. One in the month of January. January being the northern hemispheric winter, it is the southern hemispheric summer. It is mostly in the southern hemisphere, extending from one end of the earth to the other end. Then the July is the summer month for the northern hemisphere, and it is also extending from one end of the earth to the another end. And if you see, particularly in this region, Indian region, India, Pakistan region, and all this region, we can see that the ITCZ is very much high. It is over more than 20 degree north or so. Now, this is another example of the large scale, that is the planetary scale. Now we see at the equator there is we have got 3 main, say, pressure cell: that equatorial low pressure belt, then mid latitude high pressure belt, and subpolar low pressure belt. So the air is rising from the equator and then sinking over at about 30 degree north. That is the Hadley cell. Then there is the Ferrel cell, which is the air is rising around 60 degree north and sinking over the 30 degree north. Again, we have got a polar cell, which is not as strong as the other 2 cells. And we can see that there is tropopause. Tropopause is slanting from equator to the pole. It is around equator, it is about 17 to 18 kilometers, and in the mid latitude is around 12 kilometers, and at the pole it is around 8 to 9 kilometers. So this is all the global scale phenomena. Now synoptic scale is next in this. So it is not like planetary scale, is smaller than, but it is large enough. It is extending from a few hundred kilometers to several thousand kilometers, and it lasts for many days. And examples of mid-latitude cyclone, tropical cyclones, hurricanes, typhoons, extratropical cyclones, fronts, etc. Now, you see, tropical cyclone, hurricanes, and typhoons, they are the same. Their nomenclature vary from place to place. So, tropical cyclone, hurricanes, and typhoons, I have mentioned this, but they are the same. Its intensity is different, and names are different in different parts of the world. Now, I have shown a picture of satellite picture of tropical cyclones over Bay of Bengal. You can see it is extending a few hundred kilometers, almost about 1,000 kilometers it is extending. So this is an example of the synoptic scale phenomenon. Now we have got the mesoscale. Mesoscale is the next, it is the smaller than the synoptic scale, and it extends from a few kilometers to several hundred kilometers in size. This is a typical, say, phenomenon which is lasting for about an hour to a day. And mesoscale is further subdivided into meso alpha, meso beta, and meso gamma. So mesos alpha is little higher, mesoscale is middle, and meso gamma is smaller. Now, what are these mesoscale events? Like thunderstorms, squall lines, then tornadoes. Again, tornadoes and thunderstorms, same. Tornadoes are the more intense thunderstorm. Mesoscale convective system complexes, then sea breeze, land breeze, anabatic wind, katabatic wind, all this, they are all the mesoscale phenomena. And this mesoscale phenomena is very much useful for forecasting purpose, in short-term forecast, and for several hours to a day. Now, I am showing a picture of sea breeze. During the daytime, the earth gets heated, land is getting heated in the coastal area. Compared to the ocean, it is more heated, so the pressure is little lower and the pressure is higher over the oceanic area. So the cool air from oceanic area comes over the land, and this is called sea breeze, and there is the reversal at a higher height. Now, sea breeze is just opposite of it. During the night time, what happens, land gets cool and the sea is little warmer. So what happens, again cool breeze going from the land to the ocean, and again coming back, the reversal is taking place. This is an example of mesoscale system. Then another system, that is anabatic wind and katabatic wind. This is during the daytime, what happens, in the valley gets heated and the warm air goes up. So that is called anabatic wind. And katabatic wind just opposite. During the night time, the valley area is cooler, the air slides down. So that is called the katabatic winds. So this is an example of the mesoscale system. Then microscale system, it lasts only for a few minutes to an hour and covers a very small distance, about 10 kilometers. So this is the molecular diffusion, boundary layer radius, local turbulence. But as I was telling you earlier also, that there is no that rigid boundary between different scales and all these things, and the different regions of the world, they are having different. So there have been disagreement among the various meteorological services. So one example I am giving between the American Meteorological Society and WMO coverage. Now you just see that is called macro alpha, that is what is called Planetary scale, and macro beta, that is synoptic scale, then mesoscale, then we have got a microscale and viscous and all these things. So the American Meteorological Service, they say that synoptic scale is between 400 and 4,000 kilometers. WMO says that it is between 1,000 to 2,500 kilometers, 2,500 kilometers. Mesoscale, say American Meteorological Service is telling 3 to 400 kilometers, WMO says 3 to 50 kilometers. Similarly, microscale also 0 to 2 kilometers and 3 centimeter to say 3 kilometers. So there is difference, but one should remember that this is not that fixed boundary. So there is no rigid boundary between the two scales. One particular phenomenon may be embedded in another particular scale. So, and there may be, we can see when we see hurricanes, tropical cyclones, or hurricanes, we can see that there are convective, small convective system embedded in it. So this is a typical case that when they and tornadoes. We don't in our countries, in these 9 countries, we don't see that much of tornadoes, but it is a common thing in the United States. So they occur mainly with the say hurricanes. So usually the tornado reports are weak and short when it comes with the hurricanes, but still they are very dangerous in that respect. Now, this is an example of mature hurricane. Mature hurricane, we can see the eye, and we are seeing the convective activities going on a little away from this. So these are a small scale system, and the hurricanes is a large scale system. This is an example of this. Then there may be interaction between two systems of two different scales. One example of this is conditional instability of the second kind, which is called CIS. CIS is a phenomenon in which the intensification of cyclones or tropical cyclones take place. Now, what happens? The large scale system, that is the synoptic scale system, provides the convergence of moisture, and when the moisture comes and convergence takes place, they are lifted up, and because of this lifting, the cooling is taking place, and because of this, latent is released. The latent is released in this. So what happens? The pressure reduces. The low pressure is produced. Again, the convections. Again, the more convergence is taking place, and again the convergence, because of the convergence and all this, again the latent is released. So this is a continuous process in which this process is called conditional instability of the second kind. So this is a cooperative interaction between the convective system and large scale system. Now we are seeing the different atmospheric phenomena with they are of different scale, time scale and space scale. So because of these balances, some forces are balancing each other. So there is a spatial and temporal scale different order. So scale analysis is a useful method for establishing the various processes and terms of governing equation. So what happens? We estimate the magnitude of each term of an equation, and because of the relative importance, we just neglect some of the terms and keep only those terms which are of higher order of magnitude. So in this process, it is done. Now, how these scales are fixed? It is both observational and theoretical. So in this process, equations become simple. Now, what are the things we take into account? Say characteristic length scale, then characteristic horizontal velocity scale, characteristic time scale. It is known as advective time scale. This time is divided by distance upon the velocity. Then characteristic depth scale, characteristic vertical velocity scale, then Coriolis parameter twice omega sine phi. Then Rossby parameter twice omega cos phi by A, where A is the radius of the Earth. Density scale, density fluctuation, horizontal pressure fluctuation, vertical pressure fluctuation. Now, we introduce another number, quantity, that is called Rossby number. Rossby number is a dimensionless number. So it is also known as Keeble number. It is the ratio of inertial force to the Coriolis force. If you just take it into account the order of magnitude of this term, so it is the U by FL characteristics. So it shows that how important the Coriolis acceleration is. Small. Now, if Rho, that is the Rossby number, is small, that means the Coriolis force is large. That means the large Rossby number signifies that inertial and centrifugal forces are dominating. These are the things which are very important. Now, when Rossby number is large, either because F is appearing in the denominator and such as in the tropics and lower latitude, or L is small, that is a small scale motion. The effect of planetary motion, rotation are unimportant and can be neglected. That means the Coriolis force becomes unimportant. When the Rossby number is small, the effect of planetary rotation are large Coriolis force. So this is the important. So we can say that we can allow geostrophic approximation. For example, in tornado, Rossby number is of the order of 10 raised to the power 3. See, in low pressure system, it is of the order of 0.1 to 1. In the oceanic system, it is of the order of 1. As a result, tornado, the Coriolis force is negligible, and the balance between the pressure and centrifugal force, and that is called cyclotropic balance. Cyclotropic balance is commonly also occurs in the core of a tropical cyclone. Hydrostatic balance. Now, what happens? What is the pressure, atmospheric pressure at a point? Atmospheric pressure is nothing but the weight of air column above 1 per unit area. So that is the definition of the air pressure. Now, as you go up, naturally the pressure will be lower. Now, what happens when this the gravitational force is just acting against this pressure gradient force, and they balance with each other? Then we say that it is in hydrostatic balance. Now, let us do some this scale analysis, some horizontal equation of motion and say other equation of motion for different scale. Let us first do the synoptic scale or large scale. So this is the equation of the horizontal equation. I have not taken the other terms. Other terms is much lower order, so that is why I have not taken only the orders of which are equivalent more or less. I have taken that mark. So if you just see that these are the last line shows that this is the characteristic order. Now we'll take into account the synoptic scale analysis. For synoptic scale analysis, U, that is the magnitude of the horizontal velocity, is of the order of 10 meters per second, and the vertical velocity, it is much lower, that is 1 centimeter per second. That is this is a mistake. It is not 1 meter per second. I will correct it. This is by mistake. It will be mistake. Then length scale is 1000 kilometer, 10 raised to the power 6 meter. Then the height scale, it is 10 kilometer, 10 raised to the power 4. And time scale is 10 raised to the power 5. Similarly, F is 10 raised to the power minus 4 per second. Then beta is 10 raised to the power minus 11 meter inverse second inverse. Rho is 1 kg per meter cube. Then del rho by rho is 10 raised to the power minus 2. Similarly, and G is 10 meters per second if we take. So if we can write horizontal equation of motion, then if we put all this with just the last line, which we see that the order of magnitude of all the terms, the first term del u del t or del v del t is 10 raised to the power minus 4. All this term, that is the time change and the advection, horizontal advection, they are of the order of 10 raised to the power minus 4. And the order of magnitude of the vertical advection, it is 10 raised to the power minus 5. And the pressure gradient force is 10 raised to the power minus 3. And the Coriolis force is 10 raised to the power minus 3. So we can neglect the lower order term. If we just neglect the lower order term, we are getting the last two terms. That is what we call the hydrostatic balance. That is hydrostatic balance is the last two terms. So there is a geostrophic balance. We can say that this motion is quasi-geostrophic. So we say in this case the RO, that is the Rossby number, is of the order of 10 raised to the power minus 1. So, but what happens? A geostrophic motion does not contain any time derivative, so it cannot be used for forecasting purpose. So for forecasting purpose, we also take the vertical, we neglect the vertical advection term, but we keep the horizontal advection term and the time derivative also for for forecasting purpose. So for forecasting purpose, we do not take only geostrophic motion, but we can summarize this that in general it is the quasi-geostrophic flow is quasi-geostrophic flow. Similarly, if we do the scale analysis for the vertical equation of motion, we see that all the terms on the left-hand side are of the order of 10 raised to the power minus 6. Only the terms on the right-hand side is of the order of 10. So that means the other terms are very small. So what we see here, that there is a balance between the pressure gradient force and the gravity. So it shows that there is hydrostatic balance. So we can say, we can summarize that there is hydrostatic balance as well as quasi-geostrophic balance. So in summary, we can say that the motions are these quasi two-dimensional, because vertical velocity is much less than the horizontal velocity, hydrostatic, and Coriolis force is the dominant in this equation. So it is in balance with the pressure gradient force, and so we can say that it is a quasi-geostrophic. Now, let us do the scale analysis of the vorticity equation. So vertical component of vorticity is again del V del x minus del U by zeta, that is Q by L. And horizontal divergence is del U del x plus del V del Y. It is of the order of U by L. But one thing has to be remembered, for the synoptic scale motion, del U del x and del V del Y have the same order of magnitude but of opposite signs. And the order of magnitude that divergence is less than the one order magnitude in the vertical component of vorticity. So if we write the vorticity equation and put the values of these, so we see that on the left hand side, the first three terms are first four terms are having of the order of not first three terms, and the fifth term is of the order of 10 raised to the power minus 10. And on the right hand side, the 10 raised to the power and only the divergence term. So we can say, neglecting the lower order term, that this is the vorticity equation. Vorticity equation is that del zeta del U, that is the change in the vorticity, then the horizontal advection of vorticity, then the vertical variation of Coriolis parameter with respect to the latitude, and on the right hand side we have got the divergence term. That means we are neglecting the solenoidal terms, that the vortex tube term and vertical advection of vorticity. And this is only governed by the horizontal advection of vorticity and latitudinal variation of Coriolis parameter and horizontal divergence. Now we shall do the scale analysis for the mesoscale motion. In the mesoscale, U is equal to 10 meters per second, W equal to 1 meters per second. But you have seen in the previous case, the W was of the order of 1 centimeter per second. Here it is comparable, that is, it is 2 order of magnitude more. And the length scale and other scale are more or less same.
Speed.
Slow.
They want that your speed to be slow.
Because time is short. So if we put this equation again, if we put all these values in the equation, all the terms of the equation, the horizontal component of motion are same. They are of the order of 10 raised to the power minus 3. So we can say the motion is non-geostrophic. So we can say it is ageostrophic. But if we take the vertical component of the equation of motion, so we can see again that there is hydrostatic balance. Therefore, we can say that in this scale, the mesoscale flow is ageostrophic and hydrostatic. Here, RO is of the order of 1. Now, if we just apply the same scale analysis for the vorticity equation, you can find out all the terms are important. The vorticity equation in the mesoscale motion shows that all the terms of the equation are the same order of magnitude 10 raised to the power minus 8. It means that the vertical advection of vorticity, solenoidal term, and tilting term are equally important and cannot be neglected. Now we have set a convective scale or the storm scale. Here again, U equal to 10 meters per second and W equal to 10 meters per second. So what we see here in the convective scale, the horizontal velocity and the vertical velocity, they are of the same order of magnitude. And the length scale and the vertical depth scale, they are also same order of magnitude 10 raised to the power 4 meters. And the time scale is 10 raised to the power 3. Okay. And F, of course, is that 10 raised to the power minus 4 per second for the mid latitude. Mid latitude. And the variation, horizontal variation of pressure is 10 raised to the power 2, and the vertical variation is also of the same order, and the G is of course 10. So if we put this equation for the scale analysis and the scale analysis, we see the horizontal equation, all the terms are of the order of 10 raised to the power minus 2. So we can say that the Coriolis term is an order of magnitude smaller compared to accepting the Coriolis. All the terms are 10 raised to the power minus 2. Only the Coriolis term is 10 raised to the power minus 3. So we can say it can be neglected. So cumulus convection, which lasts for an hour or so, again we see the acceleration term is as important as the pressure gradient force. So the Coriolis force becomes unimportant. In this case, RO is large. It is RO is equal to 10. Now, vertical approximation, the vertical component of equation of motion scale analysis. Now, in the convective scale, the buoyancy force, that is the net upward force, plays very important role, because we have seen that the vertical velocity is comparable to the horizontal velocity, and in the case of say tornado, this thing, it is much higher. Therefore, we can apply Boussinesq's. And they are coupled with gravity to produce buoyancy term, the vertical component of momentum equation. That the vertical component of the momentum equation gets modified and becomes like this. So if we just look at this on the right hand side, we are getting that 1 over rho bar del P dash del Z, and del that is theta dash upon theta bar into G. So theta bar is of the order of 300 Kelvin, and mean potential temperature, theta dash is of the order of 1 degree Kelvin, and rho bar the mean density, that is about 0.5 kg per meter cube. So if we put all these values, we get all the terms in this equation are of the order of 10 raised to the power minus 2. Therefore, clearly the vertical acceleration is now very important, and the hydrostatic approximation is no longer applicable here. So in all the previous cases, we have seen the hydrostatic approximation, but here we don't see the hydrostatic approximation. We see only that all the terms are important. So we can say that the convective motion is three-dimensional, non-hydrostatic, ageotropic, and Coriolis force can be neglected. In this case, the RO is of the order of 10. Now, so far, all we have done is the scale analysis for the mid-latitude for all the scales. Now, we have to do the scale analysis for the tropical region. Now, if we just see, go to the tropical region, particularly in the low latitude, the 10 degree Coriolis parameter almost less than 1 order of magnitude compared to the mid latitude. And horizontal pressure gradient is also less. So in this case, RO is very large. Now, if we just see the F at 45 degree and F at 5 degree latitude, they are exactly 1 order of magnitude different. So here we can say that what we are telling in the case of say synoptic scale. Here also we are discussing about the synoptic scale. In the synoptic scale for the mid latitude, we can say geostrophic approximation is a good approximation. Here we cannot talk about the geostrophic approximation. We can say there is a gradient wind balance is there. Gradient wind balance is the three-way balance. It is the what we are getting, that the term that is the three terms are making the balance. So hydrostatic balance is also valid, except in the case of say cloud cluster or the vertical velocity scale. Now, the important thing is this: since the tropics, the Coriolis acceleration is weak, synoptic scale pressure gradients are small. Plotting surface pressure gradient in the tropics is not particularly useful. So therefore, because we see the convergence and rotation of the wind are important in the tropical circulation. So the streamline analysis is better than the say other analysis on the say if we just say the height analysis and all these things. So streamline analysis is better so that we can have better idea about the low levels, particularly the surface level and low levels. That is better. Now the vorticity equation in the tropical region, if we just see, we can see that the flow is non-divergent in the synoptic scale. So it is a very simple equation: del zeta del t plus u del zeta del x plus b l zeta del x plus beta v equal to 0. So here beta is large because near the equator the beta is large. The contrary, beta is very small as we go the higher latitudes. So it is non-divergent synoptic scale flow is on. So we can conclude that, but if we just take into account that we have taken only the synoptic scale, but if we take the mesoscale and lower scale microscale, that is the storm scale, it is more or less same as in the mid latitude belt. The equations are more or less same in the mid latitude belt. Now, most of the important thing, the key characteristic associated with weather system and disturbances at each of these scales. We should not get caught up in the arbitrary names because of the scale. So we should focus on the physical features of the forces which are working. So instead of taking that, as I told you, that there is no rigid boundary between two scales of motion. So sometimes it so happens some of the meteorologists call the say tropical cyclone. It is a mesoscale system. Some people call it is a synoptic scale system. So this type of controversy, but we should know what are the forces acting. In the case of tropical motion, what we are getting, it is say cyclotropic flow. It is the cyclotropic, the centrifugal force is very important. So we need not worry about the names of the scale and all these things, but we have to see which are the forces which are acting and what are the other physical forces. So for the preparation of these lectures, I have gone through these references. So thank you very much. If you have got any questions, you can ask me.
Thank you, sir. I request, okay, before we go to the question answer session, we will just have a quick photo session. Sir, if you can unshare your screen. Yeah, thank you, sir. Oh, we don't have Someshwar Das, sir. We will take one photo now, and then later on we can have when Das sir is here. Dr. Swagata is also not here. So, Ashwin, can you take one picture? Yeah. Pradas sir is here. Dr. Swagata, are you there? Okay. So now I request Ms. Prunal Naik, who works in IITM presently, and she is our past student of SPPU. So to please conduct the question answer session.
Thank you, ma'am. So our first question of this lecture is from Sita Pranjana Bishwajit. He is asking the question, what is the importance of scaling the atmospheric phenomena?
You see, when we are talking about different atmospheric phenomena, now we should know that which forces are important and which forces are not important. That is the importance of scale analysis. In the scale analysis, we have seen, particularly suppose we have a tornado. So in the case of tornado, which forces, we should not consider the Coriolis force. It is so small and all these things. In this case, we need not consider the Coriolis force. We have to consider the centrifugal force, which is very important. So that is the importance, that which are the forces which are important, and moreover, the equations become very simple. So if we just consider the equations of motion, the horizontal equation, the number of terms are there. And while solving the equation in the numerical weather prediction, so it will be not very easy. So if we just take into consider the forces which are acting, then the equations become simple and it will be easier to handle.
Thank you, sir. The next question is from Dr. M.G. Manoj. In hydrostatic balance conditions, how vertical motion is allowed even when the vertical pressure gradient is balanced by the gravity? What physical reasoning can be made in this case?
You see, when there is a hydrostatic balance, it does not mean that there is no vertical motion. It is a constant low vertical motion. It's not that it is the vertical acceleration that is missing. Vertical acceleration is missing, but the vertical motion is there. So vertical acceleration 0 means what happens? That the vertical velocity is constant. So that is the significance of it.
Okay. So there is another question by Johnson. He is asking, is the scale analysis and perturbation analysis are same or there is difference between them?
There is a little difference in this. Scale analysis, the exact perturbation is that suppose we say that the general motion is there, when there is a general motion. So some perturbation takes place, and because of the perturbation, some new weather phenomenon is formed. Now there is a general low pressure system. That's a perturbation. But if you want to see what are the forces acting in a low pressure system, that scale analysis gives that. But perturbation does not. Perturbation shows that this is the perturbation in the basic current system. It is like that. Suppose we have got some water in a tank. So it is steady, or water flowing in a river or in a say, pond. If we just throw a stone, so what happens? Some ripples come and some wave-like things are going. So those are the perturbations. The ripples and other things. Those are the perturbations.
Yes, thank you, sir. So there is, I guess, the second last question from Anonymous. She has not understood the concept of hydrostatic and non-hydrostatic part. Can you please explain it in short?
Hydrostatic balance. Now let us look at this. Why do you say hydrostatic balance? Hydrostatic balance means when the vertical pressure gradient force and the gravitational force, they are balancing with each other. So in this case, what happened, as I told you earlier, there is vertical motion, but not the acceleration is not there. But in a non-hydrostatic thing means the vertical acceleration is also there. Vertical acceleration is there. So in that case, we have to see that when we are considering a tornado or a cyclone, there is a lot of vertical acceleration. Whereas in the general term in a low pressure system, very little vertical motion is there, but some vertical motion is there. But in the case of, say, tornado or say thunderstorm, or say in the case of a cyclone, there is a lot of vertical acceleration. So there cannot be hydrostatic balance. Normal condition on a say good weather day, and there is the hydrostatic balance.
Okay, sir, there is one more question. Like, how does the vertical force of a tornado is formed?
You see, it is mainly because of the convergence. So the convergence is taking place. As in the case of tropical cyclone, as I told you, that cis phenomenon. Cis phenomenon is convergence is taking place because of the convergence. It is going up, and moreover, there is the You see, when we are talking about the tornado and all this thing, there are a lot of instability in the atmosphere. So the two things are very important. The instability should be there. So because of the instability and the vertical motion, the instability also, this is upward motion, and because of the convergence also upward motion.
So thank you, sir. I guess. Okay. Okay, there is one more last question. How do different atmospheric scales interact to produce extreme weather events?
Extreme weather events, like say, as I told you, extreme weather event, as I was telling you about that tropical storm. Tropical storms is giving, say, very high winds and heavy rain. There a lot of devastation it causes. Now, in this case, as I mentioned in the sixth mechanism, there are two, say, types of motion. One is that the synoptic scale system that is providing the convergence of moisture, and the other is the mesoscale system. When convergence takes place, air from moist air coming from all the places in time. So it will go up, and because of the vertical motion, when it goes up, it cools down. When it cools down, because of the cooling down, there will be release of latent heat, and that latent heat will go in the system, and it will warm that area. And because of the warming, the pressure will be lower. And because the lower this is not lower means it is compared to the environmental pressure, the site pressures. So again, there will be more convergence, and more convergence will create again upward motion. Again, upward motion means more latent heat. So it's a cooperative interaction. It will not say they are not fighting with each other. They are helping each other in this cooperative interaction between two kinds of motion.
Yes, thank you so much, sir, for answering all the questions. So hereby I declare the question answer session is over as there are no more questions. So I will hand over further things to Rohini ma'am.
Thank you, sir. There was one question, but it is not related to this particular talk. They said about a diagram which you had shown, but I'm not sure about it.
Which diagram?
I'm not sure about what diagram they want to say. Diagram shown first, the tropopause layer is lower compared to the equator and mid-latitude. So if the concentration of greenhouse gases in the troposphere increase, will it also affect the tropopause?
It will affect the tropopause.
Yes.
Even though it is not related to my topic.
Yes, yes, sir. So before going to the thanks session, I would like to give the feedback. So around 188 have registered. Candidates, participants have registered. And out of which almost 162 or 100, approximately 165 have rated it as excellent and very good. So thank you very much, sir, for this wonderful lecture. And I would request now Mr. Ashwin Zadav to please give vote of thanks.
Yeah, I will share my screen first. So on behalf of organizing committee, I would like to thank each one of you for your contribution. You for your contribution for this fifth lecture of weekly online lecture series on atmospheric dynamics and its applications to climate sciences. So firstly, I would like to thank Dr. Ghulam Rasul, member EC, SAMA Pakistan, and former DG, PMD for giving welcome address and brief information about this lecture series. My deepest appreciation goes to our speaker of the day, Professor Dr. P.N. Sen, IMD and SPPU, as well as visiting faculty at SPPU Pune for delivering wonderful and very informative lecture on concept of order of magnitude and scales of atmospheric motion. I also thanks Dr. Rohini Bhavar for moderation of today's session and Ms. Mrunal Naik for nice conduction of question and answer session. I want to thank all the panelists, EC members for their guidance and constant support for each and every minute details. I extend my thanks to all participants and attendees who joined us from across the globe, as well as finally, sincere thanks goes to team members of Savitribai Phule Pune University involved in organization of this lecture. Thank you.
Thank you, Ashwin. So,
Thank you, Dr. Bhavar and Ashwin.
thank you, sir. Yes.
Thank you, sir. Thank you.
Someshwar Das, sir. So we are, sir, you are muted.
No, thank you very much, everyone, including, of course, especially Professor P.K. Sen for the very interesting lecture. He has so much of experience that he makes the very complex thing simplified and explains it in a very simple way. Thank you very much, everybody. And I think now, is there any third lecture also by Professor Sen, or only 2 lectures were there?
No. The next lecture, which is lecture 6, will be by Dr. Ananda Kumar Karipot, who also is a visiting professor in Savitribai Phule Pune University.
Okay.
So,
yeah. So
I think he will be talking on natural coordinate system, cyclonic and anticyclonic gradient flow. So it will be on next Saturday, that is February 22.
Correct. Yeah. So thank you very much, and I think we can close it down.
Yes, sir.
Yeah.
So I will end the meeting. Thank you, everyone.
Yeah. Bye.